Good morning, everyone. Welcome back to a new talk of the sequence accelerator. Today we have as a speaker Marco Venere, PhD student at Dipartimento di Milano, who's going to present us one of his most recent research work in the field of quantum error correction. So thank you, Marco, for being here.
Well, thank you, Laura, for hosting this talk, and thank you, everybody, for joining this talk. Today, I will present you one of our last works here in the lab, which is from the QASBA, the Sparse Blossom Algorithm accelerated on FPGAs. But before starting, let me just introduce you briefly who I am. I'm a PhD student in information technology here in Politecnico di Milano and in Next Lab, more specifically. I attended my Master of Science in Computer Science and Engineering here in Politecnico, so this is my background. My main research interests are quantum computing, high-performance computing more in general, but also hardware design. During these last years, I tried to be further involved in research community in quantum computing. This is why I'm also a mentee at the Quantum Open Source Foundation. I was awarded a microgrant by Unitary Fund for a research project on integrated error mitigation techniques in the QA workflow. And finally, I've been part of the TPC member of the last IEEE QC24. Well, let's start with the description of this work. So, the topic is quantum computing, as you may have imagined, which is a novel paradigm of computation, which is spreading out in the last decades. And it's based on laws of quantum mechanics, which help us accelerate computation in novel ways. More specifically, a quantum computer is based on the concept of a qubit, and the qubit is the unit of information of a quantum device. While classical computers only are based on zeros and ones, so every bit is either a 0 or a 1, a qubit can be both of them at the same time in a superposition of states. And this enables us to find novel ways to accelerate computation. Well, let's see in a timeline what are the latest news from quantum computing. We start from the 1994, where Peter Shor managed to devise a novel algorithm which exploits quantum computing to factor integers in polynomial time. This is a very breakthrough because it enables us to understand that quantum computers can be actually useful in practice because we can break RSA crypto schemes by using the Shor algorithm. But in 1994, the number of qubits required to do that was excessively high. And in a certain sense, it is still today, because we are talking about the order of millions of qubits, which is not practically achievable, even right now. But in the next years, new research has managed to prove some effective experiments on real quantum devices. For example, in 2019, Google showed that there is a problem which can be solved in just 200 seconds on a quantum device, while it takes about 10,000 years on a classical. After the experiment from Google, there have been a great number of other experiments showing this concept of quantum advantage. So how a quantum computer can effectively accelerate computation and solve novel problems. Like, for example, in 2020, the USDC institution showed that a quantum software can run in 200 seconds against a classical software of 2.5 billion years. But most of these tasks, even though they achieve a tremendous speedup, they also only address toy examples, so problems which show the effectiveness of quantum computers, but are not really useful practically. And to address practical problems, we need to have many more available qubits. So for the future, IBM plans for 2030 to produce the first device which has 1,000 available logical qubits, which will help us solve way more complex optimization problems or physics simulation problems, for example. Yet there is an issue, and the issue for current quantum devices is noise. Because most of the devices that we are using require to run at very low temperatures. We are talking about tens of millikelvins. And in these conditions, the impact of thermal interference for any kind of electromagnetic waves is relevant. And it produces error rates both at initialization of our qubits, during the operations, so gate errors, but also when we measure the qubits, which means we read their content by losing information related to the superposition, and this is the measurement error. And just to give you a visual representation of these errors, here you can see on the left side the representation of a qubit, which is a vector in a sphere. This sphere is called a block sphere. And as you can see, this vector has two coordinates, which are the phi and theta angles. And if we consider the effect of noise on this vector, we get the red vector on the right side, which has different values for theta and for phi. So in general, what we want to do is we want to address these errors. We want to perform what is called quantum error correction and undo the effect. So to do quantum error correction, our scenario considers two different devices, which are the quantum computer on one side and the classical computer on the other side. The quantum computer has some qubits, which implement what is called an error correction scheme. The black qubits that you can see there contain data, information that we want to process in our algorithm, while the other qubits, the green and blue one, have redundant information, which we call parity, that are used to understand what kind of errors have occurred during computation. So what we do is we measure these qubits, these data qubits, and we get to what is called the injector syndrome, which is a bit string. And all the ones inside the bit string tell us, okay, probably there is this kind of error taking place on the device. There is no one-to-one match between error and bit string, which means that you don't have the certainty about the errors that are happening, but you can derive what the most likely errors are occurring during computation. So we give this syndrome to a classical computer where there is a software algorithm called decoder, which is running and takes the syndrome and produces what are the most likely error types occurring in the computation. After we decode these errors, we can derive what are the most convenient correction operations to perform to undo the effects of this error, and we execute them on the quantum device. Now, this is very interesting and very neat as a process, but there is an issue, a very relevant issue, which is for this process to take effect, we need to achieve real-time performance. So this whole cycle needs to run under a 1 microsecond around threshold, which is unfortunately a very narrow limit for current software algorithms. So the main two issues around this process are the execution time, because we have to run under 1 microsecond for this whole cycle, but also the energy efficiency. Indeed, the constrained environment of a quantum device, which is strongly affected by thermal interference, require us to use the chips which have a very low power consumption. Otherwise, the interference that they will provoke on the quantum device will lead to further errors. To address these two issues, in our work, what we did was to start from a software implementation of a decoding algorithm, which is called the Sparse Blossom Algorithm, and we profiled the software implementation. And after profiling it, we devised a hardware architecture, we called it QASBA, which is an FPGA-based decoder for quantum error correction. So we prototyped this hardware architecture for FPGAs. And this covers the entire Sparse Blossom algorithm. In addition, we also thought that current quantum engineers often do not have the required expertise to use FPGAs. So we wanted to also deploy an automation process. This automation process receives as input some high-level parameters related to the characteristics of the error correction setup. So what kind of error correction we want to use, what number of errors we want to support, and so on and so forth. And it deploys the corresponding bit stream for the FPGA by hiding completely the complexity of using the hardware design development tools, such as the ND bytes and Vivaldo toolchains. So let's start by understanding what we're talking about when we say Sparse Blossom Algorithm. So what this software does. Basically, here you can see a graph, and in this graph, there are some nodes. These nodes represent the qubits that are present on our QPU. The edges, which connect nodes, represent the errors that may trigger those qubits. So when we get a syndrome, we make the color of these nodes red, because there are some bits in the syndrome that have been triggered, telling us, attention, there is an error taking place. What we want to do is we want to find the pairs between these nodes, we want to match these nodes, and by doing that, we can understand what are the most likely errors that are occurring during computation. So, in terms of graph processing, what we want to do is we want to find a perfect matching between the errors that are on the graph. But also, the edges have some weights associated with them related to the error probabilities. Therefore, it is a minimum weight perfect matching. The algorithm goes on by building what are called regions, which are some circles around the nodes, and these circles can grow or shrink. And finally, they collide with each other. Once they collide, we find a match between these nodes. So the overall workflow of the algorithm is based on building these regions and waiting until they collide. Now we profiled this software, and we saw what the execution time is for the three main components which are present inside the module, which are the matcher, the flutter, and the tracker. The matcher is the component that takes responsibility for the overall flow of the minimum weight perfect matching algorithm. So it's the one devising the regions and controlling the growing and shrinking. Then we have the flutter, which takes control of the underlying graph. So you can focus on the required graph processing. And finally, the tracker coordinates the actions of the matcher and the flutter by the usage of events, which are produced by the matcher and the flutter and then consumed. Well, as we can see, 2/3 of the execution time are mainly taken by the flutter. Indeed, the flutter needs to process the overall graph and consider all the nodes and the edges belonging to it. And for graphs with large size, this is the main bottleneck of the procedure. Starting from the software profile, we devised QASBA, which is a hardware architecture consisting of two instructions, the load and the decode instructions. The first instruction, the load, takes responsibility of loading the content of the required instructions for the algorithm. It is run only once at the beginning, and its objective is to build the data structures based on the error correction code that we are aiming to use. Basically, it does a prefetching because we offload the generation of the data structures to the host, and then the load instruction prefetches the content of these data structures. Then we have a decode instruction. The decode instruction consists of three main stages: the stub, the MWPM, and the shutter. It takes as input a syndrome to decode and produces output the corresponding operations, corrective operations to perform. The setup stage is the one aiming to build the internal data structures for the MWPM workflow. Then the MWPM workflow, which is the most important part of the computation, implements the hardware correspondence for tracker, flutter, and matcher. And finally, the shutter component produces the final output of the device based on the computation happening during the matching. So let's go and get a detail and see how the MWPM is implemented. The MWPM sees the interaction between the tracker, flutter, and matcher. So as I told you, matcher and flutter talk to each other because they need to interact together. But they also produce events which are then consumed by the tracker that coordinates them. So everything starts with the tracker that considers the events which are in an event queue, it consumes them, and then invokes the flutter accordingly based on what kind of event is taking place. And then the flutter invokes the matcher by sending him a message. These messages tell us information of what's happening on the graph data structure, and so what kind of operation the matcher should do. And then the matcher takes action on the region data structures and sends a feedback to the flutter, which may produce some further events for the tracker to process. Once all the events are managed, the MWPM component will complete its operation and the shutter will begin. More in detail, the flutter component can process two different types of events, which are the look at node event and look at region shrinking event. The look at node event takes place where we need to focus on a specific node and see what its region is undergoing to produce a message for the matcher. Then the look at region shrinking event takes place once a region is effectively shrinking to perform further graph processing operations. Finally, the matcher component manages three different kinds of messages, which are the region hidden region, the region hidden boundary, and the blossom shattering. And these represent the three specific kinds of events that may take place during computation. And indeed, the objective of the matcher is to producing finally collisions between the regions. And the collision may happen if a region hits another region, or if a region hits a boundary, which is the boundary of the overall graph. Finally, the blossom shattering stage takes place when there is a cycle among all the regions inside the graph. In addition to this, we also devise an automation process, as I was saying before. The automation process targets the final user, which will be likely a quantum engineer. So we ask him to input what kind of target board we are targeting. So in this moment, we support the AMD FPGAs, Alveo U55C, U250, and U50, and some customization parameters, which are high-level input parameters related to the error correction code. So what type of error correction code? For example, a Turing code, a repetition code, a surface code, or a rotated surface. The distance, which is a proxy for the maximum number of errors that we want to support, and some properties related to the graph, which are the weights and the edge match strategy. Once these parameters are given as input to the automation process, what we want to do is we want to invoke the underlying development toolchain consisting of AMD Batis and AMD Vivado by hiding completely the complexity of using these tools. And that's what happens. So in final output of the automation process, we have the bit string to set up the FPGA, which is produced without further details required. So let's see how we profile the performance of our solution. Our experimental setup consists of three different FPGAs, which are the designs Alveo U55C, U50, and U250, with a target kernel frequency of 300 MHz. Our host software has been run on AMD EPYC 7B13 with 64-core processor and 512 GB of RAM. We do a software comparison against PyMachine and against Sparse Blossom, which are state-of-the-art libraries, software solutions for error correction. Let's start by looking at the required hardware resources to implement our solution. Here you can see a Turing code, and we scale the code distance. And as you can see, the main required hardware resource is the VRAM, which stands for the block RAM, that represents the memory footprint of our solution. This happens because we require on-chip memory to perform processing, since the algorithm requires a lot of memory accesses, and offloading these memory accesses to an external RAM would increase latency and so go against our tight time constraints. In addition to that, we have only random access memories. We don't have sequential accesses, which means that we cannot hide the latency of memory accesses by using streaming operations. So to resolve this issue, we require those data structures to be implemented on chip. In addition, we can look at the decoding time. The decoding time increases as expected as we increase the distance of the error correction code, because as we want to support way more errors, we need to use larger data structures and perform more data processing, but also as the error probability increases, because as the error probability increases, the number of stages for the MWPM increases as well. And as you can see, we can scale up to D+9, and we always stay under the 10 microseconds threshold, which means that we are on the good path to achieve the uptime quantum error correction performance. And in addition, for low values of distance, so for 3 and 5, we stay under 2 microseconds. we achieve about 1.2 microseconds for D equals 3. Regarding the automation process, we want to test what happens when we vary some of the parameters which are given as a high-level input. And in particular here, we vary the error correction code. So as you can see, we test the repetition code, the rotated surface, the surface, and the toric, while we vary the error probability, fixing a distance d equals to 5. And as you can see, the latency, the decoding time required by our solution varies slightly based on the error correction code. And this is due to the fact that different error correction code require data structure with different size. So the surface code is the one with the largest data structures. And the size of the data structure is a proxy for the final execution time of our solution. So the scaling looks as expected. And finally, for what is concerns the decoding time while performing the same solution on different devices, we can see that the U55C outperforms the U50 and the U250 device. We ascribe this to the achieved kernel frequency of our solution and to the optimization performed by the underlying hardware tool chain of any devices in Vivado, with the U55C reaching about 1.5 microseconds for the equals 5. Finally, let's see a comparison against the state of the art. So here we can see the decoding time where we compare against the PyMatching, which is our software baseline that we accelerated, and Fusion Blossom, which is another work that has been published during our work was taking place, actually. So as we can see, we achieve up to 25 speed up against PyMatching. Here considering a rotating surface code with D equals 5, with D equals 3, sorry. And also we are on pair against Fusion Blossom, which is the other work of the art. But as I told you before, another very important key performance indicator that we want to improve is the energy efficiency. So as we want to reduce the final thermal interference of our solution against the environment of the quantum device, we compare the energy efficiency of running QASBA on our FPGAs and running the software baselines of CPUs. And as you can see, we have a 10 times improvement against Fusion Blossom and a 300 times improvement against PyMatch, which means that we are effective in having an energy efficient solution. Okay, so with this conclusive presentation, we managed to profile and to accelerate the Sparse Blossom algorithm, and we also provide an automation process which helps end user to produce a final bit stream without requiring an expertise in FPGAs. As we proceed with the next steps of our work, what we want to do is we want to reduce the memory footprint of our solution in order to scale for higher Ds, so for higher code distances, and we also want to reduce the final latency by taking advantage of further data level parallelism. Also, what we notice is that there are still, for a number of different configurations of our solution, there is still space, there is still room on the chips to implement further hardware. So we would like to add to our solution also a control logic for qubits. And for that, we need to extend support to the Zinc Utascale Plus RF-SOC, which provides analog to digital and digital to analog interfaces. And in that way, the error correction device would also be able to perform the control logic to apply the corrective operations back to the quantum processing unit. With this, I thank you all for your attention and for listening to this talk, and I'm available for any questions. Thanks.
Thank you, Marco, for your talk. I actually have a question because you mentioned, of course, there is room for improvement in your other architectures, but I was wondering which was the most difficult part of this design process in terms of architecture, actually.
Okay, thank you for your question. Well, when we start, we want to create hardware accelerator for a software. We start by looking at the software architecture, and in this case, by matching a very complex software architecture. But also what we wanted to do is we wanted to understand how to implement the software architecture in practice on hardware, but taking advantage of the high-level synthesis tool, so HLS, which obviously doesn't support specific software routines such as dynamic memory allocation or also recursive calls. So, for example, we implemented the push-down automata to make iterative implementations of what were the recursive calls present in the software. And we also manage the structures differently in such a way that we can perform the overall graph processing without requiring external use of hardware memory devices to implement the remaining parts of the algorithm. So I would say that most of the time was very intensively focused on creating a hardware design that was equivalent to what pi matching does in software, but they can do that in an efficient way, also considering the limits of current HLS workload.
Thank you.
Thank you.
So if there is no other question, I think we are done. So thank you, Marco, for your talk. That has been super interesting, and see you to the next Friday talk.
Bye.